Thank you, Jerry. And thank you, everybody, for attending today. I will discuss about nuclear fuel study using X-ray absorption spectroscopy with an emphasis of the uranium valence state evaluation using HERFD-XAS. So today I will give you some information about what is nuclear fuels itself and give some common issues when you are willing to use X-ray absorption on this type of materials, and show that higher energy resolution fluorescence detected X-ray absorption spectroscopy can be a key tool for uranium valence state evaluation in this type of sample. And I will discuss some application examples, oxidative alteration products, and uranium dioxide oxidation. First, let me talk about nuclear fuel, and more precisely about uranium dioxide, which is the most widely used nuclear fuel in the world. And actually, it's simple ceramic at the beginning. On the left side, you have the typical pellets of nuclear fuel. And if you look at the surface of it, yes, it's just a boring ceramic. And when you put it in the nuclear reactor, there's a lot of things that happens in it. And at the end, you have a lot of cracks, different size grains, precipitates, and also void, bubbles, and everything, which makes this material very interesting. If you speak about nuclear fuel, you need to speak about fuel's life cycle, and it's really easy to understand. First, you need uranium, of course. You take it from minerals, extract it chemically in order to obtain what is one uranium oxide, U3O8, which is so-called yellow cake. And then you make the U2 pellets you can use in a reactor to produce energy. After used, you have spent nuclear fuel, but you can recycle or directly put in waste disposal. In Finland, for instance, the main idea is to directly dispose the fuel rods into canisters in copper and iron, like you have the picture here, for long-term disposal, so hundreds of thousands of years. And in France, for example, the fuel is reprocessed, recycling the interesting uranium content and minor actinide contents, separating all the fission products and as waste disposal. And the ultimate waste is put in a glassy matrix. You have a picture of it, which contains mainly all the periodic table of elements put in a canister, and then this canister will be disposed for thousands of years as well. The problem is that this material is getting more complex when you put it in a reactor, because you have in it almost all the periodic table, and the composition is constantly evolving due to the radioactivity. And this produces chemical reaction, of course. So at the end, you have several phases, defects, and species interacting together, which change dramatically the fuel properties. And the goal of safety is to ensure that the properties remains the same in order to produce energy in a safe way. On the left side, on the right side, sorry, you have secondary electron microscopy and energy dispersive X-ray mapping for molybdenum and ruthenium and oxygen in some spent nuclear fuel. And you have precipitates in it. And these precipitates are containing molybdenum, ruthenium, but no oxygen, meaning that in this oxide matrix, you have purely metallic elements, for instance, containing molybdenum and ruthenium. So you have a lot of precipitates of different nature and crystallography as well. Yeah, of course, it is a material which is difficult to characterize because of the complex composition, but also because of its radioactivity, especially after irradiation, which requires dedicated facilities. So you cannot bring these materials to any synchrotron radiation facility. The radioactivity is, for instance, if you look at fresh nuclear fuel, 5 orders of magnitudes of the same average massive activity of you and me. But if you look at spent nuclear fuel, you have 7 orders of magnitude higher of activity, which is, of course, making the experiment on these materials more complicated. Usually, you have to use telemanipulator to deal with such materials on a safe manner. So, studying these materials, you can use X-ray absorption spectroscopy because it's a very useful technique to have information on valence states of elements and the local environment. But first, you need to find a beamline accepting such type of sample. Luckily, in Europe, we have at least 3 different beamlines accepting such type of materials and actually being dedicated to these type of materials. The first one is the Mars beamline at Soleil Synchrotron. So in France, just in south of Paris, and you can bring very highly radioactive materials in there, and especially spent fuel is accepted in it. So this is a unique facility. The energy range is mainly situated in the hard X-rays, but actinide images, so between 3 and 5 keV, are also available depending. Hard X-rays is mainly the goal of this type of beamlines because you need to go through lots of windows acting as a safety barrier around the samples most of the time. So that's why soft X-rays are less used. The second beamline is a Robel beamline at the ESRF. There you can go to a little bit less of radioactivity, but this beamline has been built to be dedicated to actinide studies, and especially the L3H at the beginning, but now they have an emission spectrometer which allows them to look at the actinide images as well. The last one is the cadet beamline in the small synchrotron Anka in Karlsruhe in Germany, and this one you have the possibility to bring some fissile elements in your sample with a very nice quantity available possible, and the energy range is quite big, so you can study lots of elements in your fuel, for instance. The counterpart is that this beamline is dedicated half of the time to catalysis and half of the time to actinide research, so there is a little bit less of beam time available for fuel studies. And we are quite lucky because all of these beamlines are equipped with emission spectrometer. I will show later why it is so important for us. So then you have the beamline and you have to deal with a lot of paperwork in order to have the possibility to bring your samples there. The one who are used to bring some additional samples into the beamline, which is an unusual way of doing. It's impossible in the case of such sample because every milligrams of samples have to be declared beforehand, and special transportation have to be considered. So if the experiment is not going well, we are losing beam time, actually. The sample transportation itself is quite expensive as well, but the most problematic thing is that the time delay between the sample you have in your dedicated laboratory and the beam time you obtain, which could be 6 months later. And meanwhile, the self-irradiation of the sample due to the radioactivity of it is affecting what sample you are going to measure. So if you are measuring, let's say, using XAS at the laboratory, for instance, when you go to the synchrotron, it's more likely that your sample will be a little bit different. Hopefully, now, thanks to laboratory scale X-ray absorption spectrometer, we can examine our samples in a way that it is directly comparable to what we are going to measure at the synchrotron, which makes our life a little bit better. And you can take a look to these 3 recent papers, which are dealing with nuclear materials characterization using laboratory scale devices. During the experiment, issues are not ending, because most of the time you cannot do transmission mode because of the heavy matrix containing actinide, and you cannot prepare the sample easily, and by the fact that other elements inside your sample are low concentrated. So fluorescence mode is usually performed, but in fluorescence mode we obtain we have sometimes, because of the high crystallinity of the sample themselves, elastic scattering, saturating detectors from time to time, so randomly. And we have a lot of fluorescence lines overlapping. On the right side, this picture, you have an example of what you can measure in fluorescence mode without the right energy resolution for separating the lines. For a U2 sample doped with only 11 fission products. So it's not all the fission products are in it. And you can observe different edges from cerium, lanthanum, barium, neodymium as well. And this huge peak here is due to the elastic scattering arising randomly. So just because of the geometry of the sample and the fluorescence detector being in the wrong angle, but you cannot predict it actually. And to solve this, you need to achieve a resolution below 30 electron volt, but it's impossible with using the best silicon drift detector or solid state detector. And another problem is that if you look to your sample directly, you may saturate or kill the detector by itself just because of the radioactivity of it. So it's better to look at the sample indirectly, and to do that, X-ray emission spectrometer is a very nice solution for that. After the experiment, you still have some problems, especially because there is the self-absorption correction, which is often mandatory because it's an AV matrix anyway. And you have additional issues when you want to study actinides. The cohort lifetime of actinides is very large. You can see on the right side some uranium L3H spectrum for different compounds with different valence states or valence state mixer. And you see all the features are really broadened. It's because at uranium L3H, the cohort broadening is about 8 electron volt. So you are just smoothing everything you are interested in. At MH, it's a little bit better, but at the end, you still have the chemical shift is in the order of 1 electron volt, so you are just smearing everything. There is also some other difficulties, especially for XAS. Multi-electronic excitation at the actinide L3H is always present, more or less, but still, and you have to correct it. And the crystal field splitting in such a compound is usually in the same order of magnitudes than the chemical shift. So everything is complicated with these materials, but yeah, it's fun to study them. So one solution to solve these issues, or a large part of it, is using X-ray emission spectrometer. The one which are usually found in the beamline dedicated to radioactive materials is based on the Roland circle and the Yuan approximation, which allows you to focalize the ray of interest into a detector, shielded, so then you are sure not to destroy the detector by having highly radioactive materials in vicinity. You remove a part of the background this way, so you increase the signal over noise ratio. The geometry is based on wavelength dispersion of the emitted fluorescence using, for instance, silicon or germanium band monocrystals. And you can achieve high resolution for the separation of the fluorescence lines of the sample containing almost all the periodic table. You have here a picture of the emission spectrometer consisting of 4 crystal analyzers on the Mars beamline. The detector, the beam is coming this way, hitting the sample here. Here, the emission spectrometer is without any shielding for highly radioactive materials, but in the near future, there will be a shielding here in order to protect the people walking around as well. Of course, if you use an emission spectrometer, you are not exactly in the X-ray absorption regime. We are in the so-called photon in, photon out regime, which is a two-photon phenomenon, and which is something in between X-ray absorption and X-ray emission, mainly resonant inelastic X-ray scattering. On this picture, you have the excitation energy, so the incident beam energy, and the final state energy, which correspond to the difference of the fluorescence line energy and the excitation energy. And the high energy resolution fluorescence detected XAS is typically cut along the diagonal here, which, thanks to the fact that you are in a two photon phenomenon, you virtually reduce the cohort broadening of the feature you have here, which is well seen in this picture of the sodium uranate measurement, where the black line is standard X-ray absorption measurement and the red line is obtained using HERFD-XAS. And you can see we can resolve the two peaks corresponding to the crystal field splitting of the 60 electrons in this compound. On the right side, I put this in the sense that what we are going to observe actually using this method is a first transition of the system from the ground state to an excited state with one hole in the 2p electrons. Then we are collecting the emission line, which is emitted when the excited state is reaching less excited states. There can be many states, and these states are related to the transferred energy here. You have all of these depending on the oxidation states of uranium for L3H and M for H. And what has to be mentioned is that for the L3H, usually the uranium 5+ is a little bit more tricky to measure because the shortening of the bonds, of two bonds in the uranium environment, makes the energy level of uranium 5+ a little bit less than uranium 4+ changing, which makes life a little bit more complicated, as demonstrated by Neil Hyatt a few weeks ago in his presentation. So I'm finished with the broad overview of it. So if you have any question, I will be happy to answer before going to the example.
Thank you, Rene. So two questions. One, you showed that there was the steel canister and then the copper overpacking when storing the nuclear fuel for long-term in Finland. Do you happen to know the reason for the choice of that geometry and the copper on the outside?
For the geometry, no, I don't know the answer, actually. I'm working on fuel repository only for a short time right now. But for the copper and the iron, actually, the inside is iron because when water will get into contact with the iron, there will be the presence of iron will reduce the solubility of the spent fuel itself. So it's kind of a chemical buffer.
I see. Okay.
And for copper, maybe because it's it's reacting. It's probably more stable than other type of metals, maybe.
I see.
As a function of the price as well, because it's just a question of price and compromise between the price and the safety.
I understand. The second question is whether you have any suggestions for beamlines in the United States so they can do HERFD and RIX on uranium, on actinides.
I don't know, actually, because usually in that field you are not looking to beamlines so far away because it's really a pain to fill all the paperwork to bring some so radioactive materials across borders.
Yeah, I know that SSRL has a beamline that takes rad materials, and also sometimes at APS. Maybe someone else can comment in the chat, and I'll repeat that as we move on to the next question. The last question is, you showed that wonderful HERFD cut in your last slide before the questions, where you were able to see the crystal field. Yeah, that one with the crystal field splitting. And the question was whether instead of doing HERFD in this kind of system, you could have tried deconvolution of the core whole lifetime, and whether you think that's worth pursuing.
For this, yeah, for this specific sample, it should probably work, the deconvolution. But if you want to go to some crystal field splitting, yeah, less important than in these materials, the deconvolution will be not able to do it correctly, I guess. There is a paper from Kristina Kvashnina, I don't remember exactly which year, but a few years ago. She observed the crystal field splitting in U2, which is impossible to distinguish anyway in the standard type of spectrum.
All right. Someone commented that SSRL 10-2 has optimized their beamline for rad materials. One more question. Whether M-line emission for detection helps with overabsorption by reducing the probe depth. Matthew, do you want to ask that question? I may not be phrasing it properly. Are you available?
Yeah, here I am.
Oh, great.
Yeah, the idea is what you've been calling self-absorption is it can be reduced if you have, well, it's caused by the probe depth varying with the energy, so that as the sample gets more absorbing, you probe fewer atoms. And so if you use M-line emission, then it's the fluorescence that controls the probe depth, and therefore that gets rid of it. So in this slide, it looks like you're using the M-line emission.
Yes, that's true. It's the M-line emission we are using in this slide.
And that would be a good reason for using the M, even if it might be less sensitive and less signal.
I'm not sure I follow. If you do the M-edge spectroscopy, then the sample will pretty much always look thick, and you'll have strong self-absorption.
Right, but here he's doing L-line, doing L-edge spectroscopy, but with the M-line being used for detection.
I don't think that's right. He's in air. What line are you using?
No, it's L-alpha 1 line, and actually we are close to, because it's the final state energy, and the final state is we have a hole in the M.
Okay, I was misled by that, by the final state energy.
Okay, all right, Rene, you should continue for the next part of the talk.
Okay, thanks. So first example I wanted to show you is the oxidative alteration products, and especially some very complicated chemical formula, uranium hydroxydihydrates, which are produced when the uranium dioxide is dissolved or is alterated in oxidative environment. It's this type of compounds can play a predominant role in the radionuclide release from spent fuel into the environment during the long-term disposal. And the chemical reactivity of uranium dioxide is mainly controlled by the valence states of uranium in these intermediate compounds or products of the alteration, and it's generally the case in every geochemical processes. These type of materials have a layered structure with several non-equivalent uranium local environments. So mixture of uranium 4, 5, 6 mixed together, and that makes extra absorption useful, but more complicated to use in the sense that you need a very high sensitivity in order to determine the valence state of these compounds because they are required to understand the long-term disposal safety of the spent nuclear fuel. Because if you stay in uranium 4+ state, most of the time the dissolution will be very slow, several order of magnitudes below than if you have uranium 6+ or 5+. So meaning that the release of the radio element inside the fuel itself will be very slow compared to the time of the disposal. One type of this compound I studied a few years ago is the nickel and uranium oxohydroxyhydrate, which shows the typical layered structure you can see on the right side. And it has 5 non-equivalent uranium atoms. 3 of them shows a pentagonal bipyramid, a type of coordination. The 4th show a square bipyramid type. And in all of these 4 uranium environment, we have uranium-like uranium oxygen short bonding, which means typically uranium 6+. But for the 5th non-equivalent uranium, we have a distorted octahedron, and despite of being very close to uranium, so uranium-like, these 2 in blue bonding are very long. So it's impossible to say just using this that uranium is in the 6+ state or in the 5+ state. So it was important to see what was the valence state of this compound. The first step was to use standard XAS at uranium L3H because that's, yeah, it's what everybody is doing in such type of materials. And fitting this was not easy for several reasons, but we succeed in confirming the XRD-deduced structure mostly. But we have some problem, as discussed a few weeks ago by a presentation in this class meeting, with the fact that we have multiple uranium oxygen and uranium distances. So we need to group them for achieve a fitting using minimum fitting parameters. Another problem in this type of sample is that we observe a dramatic disappearance of the uranium-uranium signal due to the fact that we have destructive XAS path interferences due to the fact that there is several of them and with distances leading to destructive XAS signal. But we succeeded in measuring it. Then we perform HERFD-XAS at uranium L3H following the L-alpha-1 emission line and using a silicon 880 spherically bent crystal analyzer on the Hubble beamline. And you have here the corresponding spectrum, and compared to what I showed previously, we can see that there is more sharpened features, and we can more easily find what is the valence state of the compounds we are measuring. Actually, in our case, it was pure uranium 6+. We do not observe any shift close to the uranium 5+. The problem is that with uranium L3H, the spectrum are polluted by quadrupolar transition. So the electron is directly probing the 5F electrons instead of the 6D. And this probing appears to be just before the 6D white line, making a kind of a shoulder or pre-edge in the spectrum. You can take a look to the paper by Vitova on this topic, when they demonstrate that the quadrupolar transition actually affects a lot the valence states evaluation in the standard uranium L3H, and it's also problematic in the case of uranium 4+, 5+ determination using HERFD-XAS. In our case, it was also present in that compound, because if you look at the calculations using the FDNS code and the crystal structure deduced before using the XAS results and XOD. The quadrupolar transition is needed to allow better accuracy between the experiment in blue and the calculations of the XAS signal. Because of the quadrupolar transition, there is something that the resolution of the valence state is less good than expected. So we try to use ERFD at the uranium M4H and following the M beta emission line. And you have the results we obtain here. So you have typical compounds containing uranium 4+, 5+, and 6+. And you can see that the resolution is quite nice enough to separate well uranium 4+, 5+, and 6+ with 3 different positions of the white line. And this allows us to confirm that this compound is purely uranium 6+. And one benefit is that it's, as far as we know, this is only pure, oh, sorry, there is a mistake here, dipolar transition from 2p to 5f electrons. We are directly probing the 5f electrons. And the resolution is lower than the chemical shift expected for this type of samples, which is very nice. So I can have a quick question before the last part of my talk, if you wish. Can you hear me? Jerry?
Sorry, I was muted. I apologize. I was saying we're going to wait just a minute for questions, but I had a question for the EMEDGE HERFD. I thought it was lovely data. I wondered if you could just tell us about the spectrometer and how air absorption was dealt with.
Oh yeah, so the spectrometer was half a meter UN type spectrometer. It was actually the same we have I showed before on the Mars beamline. And we had this time 2 crystal analyzer of silicon 220 and a KTEC detector, standard one. And for limiting the self-absorption, we used a helium bag, helium containing bag, just in between.
Okay. All right, seeing no other questions right now, why don't you continue? This is beautiful data.
Yeah, thank you. So the second example I wanted to show you is uranium dioxide oxidation, because it is likely an issue for all of people using uranium dioxide as fuel, because it's likely to occur during any disposal, because uranium dioxide is not the most stable uranium oxygen compound, because it will have the natural tendency to oxidize towards uranium-3 oxide, actually. This oxidation is happening through several steps or several intermediate compounds. Usually you may have U409, then U307, U205, U308, and then U3. The big issue with that, okay, adding oxygen is not a big deal most of the time, but we have a phase transformation around U205 because we are changing the cubic crystal structure of uranium dioxide towards layered crystallographic structure of U3, so around U305. And this change in the phase is producing 36% volume increase. So which have something like I like to call a popcorn effect, like here, because you will increase very highly the volume of the uranium dioxide pellets, and which have an high impact on the cladding integrity, because you have cladding materials around it, and you need it to be without any cracks or too much pressure from the inside in order to be sure that all the radioactivity or radioactive elements stay inside it. You have here some XRD at high temperature measurements performed on uranium dioxide oxidation, and you can see the change in the crystal structure going from U2 through U308. So this oxidation has to be, of course, avoided for safety reasons, but the problem is that the intermediate compounds are poorly known so far. Why is it so? Actually, the valence states of uranium is not very well determined for the intermediate compounds. For U2, it's very well known because it's the basic material for nuclear fuel, and it has been well studied for, yeah, let's say half a century at least. But then it's getting more complicated, and at the end, the final product is well studied as unknown because it's the most stable compound of uranium oxide. U2O5 is quite also a special case because it should be, in principle, pure uranium 5+, but X-ray absorption on this sample has never been measured yet, as far as I know at least. It has been produced only recently in a thin films using high resolution XPS experiments as described in this paper. But for the rest, U409, U307, and U308, actually you have several possibilities of valence states mixture in order to reach neutrality in these compounds. In the recent years, Kristina Kvashnina and collaborators have studied U409 and U308 using uranium M4H, and they have allowed us to eliminate some possibilities, meaning that U409 is containing a mixture of uranium 4+ and 5+, thanks to the ability of the MH in HERFD-XAS to separate well the different valence states. And for U308, it was a mixture of 5+ and 6+, as demonstrated. One question was remaining, U307, and actually we were able to synthesize pure U307 samples, which was not made before, actually reported. And they were first studied using X-ray diffraction and electron diffraction to refine the structure of it. And it has a very large structure and complex structure based on the cubic structure fluoride of U2, but with the long range order of oxygen clusters formed by the excess oxygen, the so-called cube-octahedral defects or clusters. You have it in this picture where the excess oxygen are in green and the standard oxygen in the U2 lattice are in red. The thing is that these cube-octahedral excess oxygen clusters are making long-range orders, and these long-range orders are difficult to see even using XRD. And it was possible to study them using XRD and so on. First, we did XAS like previously because it's the first step. And we studied it using two different crystal structure. The first one is U307 primitive cell based on a different crystallography structure than the fluoride structure. And it shows that the fitting was not good at all. And by using U307 based on a very big cell, but an average superstructure of the U2 structure, it was possible to obtain a good fit. Of course, it has been difficult because there is multiple uranium oxygen distances. So it was needed to group some uranium oxygen path. Here you have the different average number of uranium oxygen bonds in the compounds, the distances, and we grouped them in two different groups, short, medium, and long distances. By doing that, we obtain very nice XAS results and fitting, which confirm the presence of oxygen cuboctahedral clusters in this compound. Then the question of the valence states was needed, and we went directly to the uranium M4H because of this efficiency. Here you have the spectrum, so of all the intermediate states which were available at that time. So uranium dioxide in black, purely 4+, then U49, 4+, and 5+. So you have the second peak of the 5+ appearing here. Then U307, which was found to contain 4+ and 5+, but no 6+. And U308 and U3, which contains uranium 6+. Sorry. So the fact that we observed a no uranium 6+ local environment in this compound using HERFD-XAS, because of that, we need to reevaluate electron diffraction results in this sample because we assume at the beginning that there was short bonds in that. In addition, neutron diffraction data are currently analyzed in these compounds in order to try to understand better the structure and essentially the large long-range order of the oxygen cuboctahedral clusters. So at the end, it was possible to study uranium dioxide oxidation and to follow what the valence state's behavior is during this oxidation, at least for the intermediate states which are stable enough to be measured. So it's a two-steps process. The first is oxidizing uranium 4+ into 5+, and then when every uranium 4+ has been changed into 5+, start to oxidize them to 6+. So you have here the measurement we made and the different concentration of uranium valence state, 4+ in black, which start to decrease as when you increase the oxygen content from uranium 2 to U205. Uranium 5+ is created at the expense of 4+, and then when we reach U205, which is supposed to be pure uranium 5+, we start to create 6+ at the expense of 5+. In between these points, it has to be confirmed, of course, if we want to do that, in situ HERFD measurements, so measurement in temperature in controlled atmosphere will be needed, but it's not the big deal right now, especially with the emission spectrometer, which allows to have measurement performed in, let's say, in half an hour or so. And this two steps oxidation behavior has been in good agreement with when you dop the uranium dioxide with some aliovalent fission products like lanthanide. And if you do that, you observe that uranium 4+ is at the beginning changed in 5+, and when all the 4+ are already changed, only then you start to observe uranium 6+. So HERFD-XAS is really a powerful tool for uranium valence states evaluation in compounds, even when the compound contains several non-equivalent uranium oxidation states. So whatever the mixture, it is working well. Whenever it's possible, M edges must be preferred because there is no quadrupolar transition in it, and the resolution, let's say the ability to separate the valence states is better. is better than the valence state energy shift. The uncertainty in the composition has been found so far to be around 1 to 2% in the valence state mixture, which is quite nice already. And there is almost no features depending on local structure observed so far on the white line. So you can only use the white line to determine where the valence state is in your compounds. So this is all for today, and I will be happy to answer some additional questions.
That's wonderful data. The image looks very powerful for looking at the uranium oxides, and the in situ study. I'll bet that's going to be great fun. We do have a question concerning the image work. How was self-absorption dealt with? Was it a thin film sample?
It was not film sample. It was just regular pellets, actually, and very surprisingly, we did not observe so much effect of the self-absorption in these samples. Probably because at the images we are looking to an emission line, which is which one it is, I don't remember, sorry, but I think it's N to M. So then the self-absorption is limited probably mainly by the fact that this emission line cannot reach outside of the sample unless it's going from a very close surface.
Got it, I understand. Another question is, can you comment on the choice of M4 versus M5 and whether there's overlaps in the spectra or there's good enough separation?
Actually, M4 has been used mainly because of the availability of the silicon 220 and the fact that the angle is better, the Bragg angle is better for the emission spectrometer. M5 can also be used without any big problem, I think. I think we measured sometimes M5. I don't remember exactly. I have probably some spectrum at M5, but well, if it's possible, use M4. For other actinides until plutonium, I guess you need to stay to M4 and go to M5 when you start with americium and higher. But mainly because of the scattering angle on the crystal analyzer.
Okay.
And for the energy, the self-absorption at the M5, not the self-absorption, sorry, the absorption through the air or the helium bag or whatever will be higher for M5 anyway. So yeah, you have less photon.
Okay. John Vincent, you've got a question?
Yeah. I think I missed this, but could you comment again on why you're worried or why you're trying to avoid quadrupole transitions or a contribution from the quadrupole transitions?
Okay, yeah, the quadrupole transition is problematic in the sense that, let's go back to this. Yeah, in the sense that depending on the uranium valence state, the 5F electrons will be shifted as well, as we can see on the images. And typically we have these images appearing here just before the white line. The signal corresponding to the quadrupolar transition will be the 5F, and they will appear here, but they are going to shift as a function of the valence state as well. So if you have a mixture of the valence states, actually you will have two peaks shifting probably in different way. So it makes life a little bit more complicated to find where the valence state is. Is it clear, or should I?
No, that's clear. And I guess the follow-up is the modeling, you know, the FT-MES able to actually help you back that out, or does it just make it It's just make it more complicated, and it's easier if you can avoid it.
Yeah, it's easier if you can avoid it, but actually until now, FDMS and FEF as well, I test with FEF, and both are working quite well for uranium L3H, if you take into account the quadrupolar transition or not. But for the MHs, there is still some difficulties. At least FDMS I tested so far is not reproducing well the spectrum for uranium 4+ and some of the 5+ compounds. For uranium 6+, everything is fine, but you have not the problem with the F electrons and the 5F electrons, and every problem arising when you deal with the 5F electrons using DFT calculations and so forth. So yeah, for the 6D, it's okay. So if you can deal with the quadrupolar transition, and if you are going to make calculations, it's okay. You are pretty sure to obtain very nice results. For the images, it's still complicated. So that's nice. We are not to deal with additional transition in the spectrum, so we can have direct information.
Okay.
All right, a couple more brief questions, and then we'll stop for today. One question is for the L3 edge measurements. Are you able to determine the 2p3½ ionization energy, which is buried under the higher energy edge side of the white line?
Sorry, can you repeat, please?
It's a question about trying to get out the 2p3½ binding energies, ionization energy, rather than the white line position.
Yeah, we didn't try that, but could be.
Okay. That's all right. The last question is, it looks like there's a nonlinear dependence of the white line position on oxidation state at the M4 edge. And the question is if it's normally attributed to differing hybridization schemes or localization of 5F electrons or what? So if you go to M4 data, yeah, go ahead.
Actually, yes, this nonlinear behavior of the 5F position is mainly due to the fact that there is interaction of the F electrons and hybridization with the 6D and the oxygen 2p as well, depending on the compounds. Actually, on Rene, you have splitting in different the 5F electrons for uranyl type bonding. You have these two additional peaks here and here in the spectrum for the beta U3, for instance, and for the huge compound here, which are due to the fact we have uranyl bonding in it. So the uranyl bonding can affect new features, but also a little bit of the shifting. Actually, for the beta and the nickel, there is difference in the positioning here of the white line. They are not perfectly superimposed. This is still intriguingly, yeah, we do not understand yet exactly why it is so, but there is at least something happening for the 5F electrons due to the hybridization between the 5F, the 6D, and the oxygen 2p. This is well known in the L3H, where the uranium 5+ is mainly almost observed below the uranium 4+, before going back to the 6+, just because of the uranyl tap bonding or shortening of the oxygen bonds make shifting of the 5F and the 6D at lower energies, but not in the same manner. So there is a lot of different effect in uranium, for sure. In addition to the crystal field splitting and so on, which affect as well the F electrons somehow.